All right, so our next speaker will be Masoud Mohseni from Google, and he'll tell us about inhomogeneous control of quantum phase transitions.
Thank you. So sorry for technical difficulties. This is the room has been renovated. This is the first event after renovation. So this session is supposed to be on various inhomogeneous protocols to navigate through first and second order phase transitions. You already heard two talks from D-Wave that addressing this issue for first order phase transition. I'm going to discuss how we can engineer a non-trivial inhomogeneous path to basically navigate through a second order phase transition and minimize the density of defects. This is a work done in collaboration with Mark Rams and Adolfo Del Campo, where Adolfo is in this audience. So I'm going to go through a quick description of the talk. I'm going to start with the motivation and then introduce quasi-adiabatic mechanism for people who have no background. Then I discuss how we can go beyond quasi-adiabatic mechanism. The idea is that can we beat that limit or prediction by quasi-adiabatic? And that's kind of the idea of engineering inhomogeneous second order phase transitions. And then I discussed that actually you get a new class of universality, which is universality of critical fronts. And I conclude with possible application to approximate optimization. So the goal is to design a protocol that is not necessarily care to get a ground state of an annealer, but to stay in the low energy sector. So basically, there are issues with trying to solve the problem Hamiltonian get the ground state is that first, it's very hard for a hard problem, and the second is it's actually not needed. For many applications in machine learning, knowing the ground state is actually not good. If you want to apply machine optimization for machine learning, if you get the ground state, most of the time you're actually doing overfitting. So it's not a good idea. So the idea is how we can engineer a control field that can be constructed in homogeneous in time and space such that it allows you to open up a gap between low energy sector and the higher excited state. So I quickly go over a brief review of quantum phase transitions. So this is a phase diagram with as a two parameter of G and T. T is the temperature, G is your control parameter. Usually you can change it. You can consider this is the coefficient associated with the transverse field. And the second term is your problem Hamiltonian. And you come from a very large value of G's all the way down. And at certain value of GC, you get a phase transition. And this is here in this talk, we are going to consider only the zero temperature limit. Vadim at the last talk in this session is going to address the final temperature effects and environmental effect for a spin chain. So the issue is this: the core of the idea is related to the physical property of quantum system at a quantum critical point. So we can introduce this new parameter, epsilon, a dimensionless parameter that gives you the distance to the critical point. So remember at GC we had the system experience the second order phase transition. So you introduce G minus GC and normalize it. The thing is that if you come from a large value of G and as you approach to the value of GC, the epsilon goes to 0, and this is correspond to kind of an impulse regime between two adiabatic evolution. So basically you start adiabatically following the dynamics, but then suddenly things are changing and the system stops responding and you have this kind of phase transition. And what it means is that the gap is vanishing and the correlation length is blowing up. And this is with two different critical exponents, which is nu and z and nu. The idea is that that led to the quasi-adiabatic mechanism is what happened actually near critical point in the vicinity, not exactly at critical point. The idea is that for any finite time, quench time, you are not going to ever actually experience what you believe happens at critical point because the system is going to freeze just before you get to the critical point. So this is just quasi-adiabatic mechanism in one slide. And it's very simple idea. It's a phenomenological basically theory with two assumptions. The first assumption is that the time that the system can respond adiabatically, it's 1 over the gap, and that's kind of a very decent assumption. The second one is saying that the value of the epsilon, you can expand it linear over time with the coefficient, which is 1 over the quench rate. And this is, that's all. And all you need to do to have replace t from this first expression to the second one and just solve it for epsilon. And then you get an expression for epsilon as a function of tau q. And so tau q is your annealing time or your quench rate. And you can solve this for t and get something that is known as the Quasi-adiabatic time or the freeze-out time in the impulse regime. And again, it's a function of tau q. You can use the value for the epsilon and find the correlation length, which gives you this expression. And the inverse of correlation is your density of defects, which is this exponent is the dimension of the system. And this theory has been pretty successful, both experimentally and theoretically. For 1D, you can do exact solution and see that you get this relationship, which is within a prefactor completely consistent with the prediction of Quasi-adiabatic. So the core idea I want to emphasize here is that the idea is that just before you get to this kind of quantum critical point, you actually never get to the point. Just before that, you go to excited states, you have a finite number of defects and finite range of correlation. And the state that you leave after this quantum critical point is exactly what you freezed out before that region. So you start adiabatic evolution. So here you start the adiabatic evolution with the excited states that you left when entering that regime. So for a quantumizing model, you can write this Hamiltonian. This is for a cleanizing model. This is the simplest possible system. You can see this like a phase transition. And there are two different orders, like a paramagnetic or a symmetric phase and the order phase. And you go through a phase transition with any rate of finite quench for this kind of system that thermodynamic limits they are gapless. Basically, at any finite time, you have a possibility of defects or kinks. So the idea that I think inspired my work on this is that how we can improve this performance, basically reducing the excitations or topological defects by driving the system in a non-trivial way using the different paths. So there have been some works on using various paths for annealing, but all of them are based on some random initialization of some Hamiltonian, intermediate Hamiltonian. So this is, I think, to my knowledge, the first constructive way of using a non-trivial Hamiltonian, basically a programmable approach to annealing. So I should mention that the idea of inhomogeneous Quasi-adiabatic has been applied to a system in absence of disorder. This is the first time that we applied it to disorder system. So you can consider it like a spin chain, that is sitting spins from 1 to n. And here it's a schematic way of the simplest possible inhomogeneous schedule. Is that here the spin 1, 2, 3 already experience phase transition. Spin 4 and 5 are in the middle of simultaneously experiencing phase transition. And spin 6, 7, 8 have no clue what's happened. As far as they're concerned, nothing happened. So this is in contrast to a homogeneous schedule that you start from GI, like this dashed line, which is uniform everywhere, and you just come down, and at GC, this dashed line, you get a phase transition everywhere. And so I argue that that's, generally speaking, suboptimal for almost every case. So there is a non-zero value of a slope, which is this alpha that is optimal schedule. So you can smooth this profile with this function, and for a small alpha, you can just consider it linearly related to like a n and t. So, and this is your basically epsilon, the parameter that describes the critical point. And it means that if the n, the location of a spin is where, at any given time is equal to vt, it's 0, so you have phase transition. So you have phase transition in a space at various times. So this is a space-time separated event. So for n much smaller than vt, these are the things that are already in the order phase, already experience phase transition. In the spins that are way over there on the right-hand side, n larger, much larger than vt, you already, the system is still in the symmetric phase and has no clue. But it's interesting that just a little bit in front of this critical front, there is a penetration depth. So the spins a little bit in front of the critical front, get an insight of what happened in the broken symmetry phase. Because if you diagonalize this Hamiltonian, you get kind of free, non-interacting quasi-particle, fermionic quasi-particles, and those are actually moving. So if you move the critical front smaller than the velocity, group velocity of those particles, you get longer range of correlation. That's the core idea. So to see this better, consider a fixed spin in the chain, and then you can write this epsilon in this form, which is like this is the coefficient of t. Remember, it's just your inverse of quench rate. So then here the global annealing time becomes related to this kind of inhomogeneous parameter, this new like many body parameters alpha and v. And so the idea is that if your speed of this critical front much larger than v group velocity, basically you are in homogeneous regime. In homogeneous regime, your alpha is 0, the slope is 0, and your velocity is infinity to get a finite quench rate. But if you go smaller than group velocity, you get a new physics. So basically, you get longer range correlation. So, and this might be, you get this impression that this is the necessary and sufficient condition, but that's not true. So there is actually a speed that is slower, and it's related to the, kind of Kibble-Zurek understanding of a different speed scale that information can transfer, and it's slower. So to see that, you can define the velocity of the information transfer as like dividing correlation lengths over time. So the correlation length is like the Kibble-Zurek correlation lengths that describe how much correlation you have, and time is Kibble-Zurek time. These are like length scale and time scale that things happen in a Kibble-Zurek world. Okay? So you divide it, you get Kibble-Zurek velocity. And this velocity, you can plug in the relation for like a standard Kibble-Zurek and then use this expression for inhomogeneous version, and you get an expression for velocity as a function of alpha. So with the control parameter, you can change the speed of information. So you're controlling a many-body system with effectively a many-body parameter. So it's not based on a microscopic degrees of freedom. And for z, this is critical exponent. If it is larger than 1, you get non-trivial effects that v can be increased by alpha. And more interestingly, you can look at it at another perspective, is that you can actually effectively, you're introducing a gap for a system that is gapless. So basically, by putting the delta as an expression that you have in Kibble-Zurek and just plug in epsilon and the relationship that Tokyo has with the alpha, you get an effective gap expression. So based on this expression, you would say, oh, that's great. I just increase the alpha and I just open up gap as much as I want. But that's not really the case, because there is another parameter that you have to take care of. It's the diffusion length into the symmetric phase. And this is because there is a finite penetration depth into that phase. Basically, this is given by effective Kibble-Zurek mechanism, which is related to this effective gap that I introduced. And so in a way, if you choose alpha too big, you get a good gap, but you have like very small penetration. For the trivial case of an inhomogeneous protocol, that you just do one spin at a down update on a linear chain. And that's just an inhomogeneous schedule, but it's a trivial one, because the penetration depth is just one spin. So you cannot capture any non-trivial correlation. And that's suboptimal. And the alpha 0, which is you put all the spins at the phase transition, is suboptimal too. Because you get bounded by the global gap. So now this opens up a possibility of a different gap, not the gap of the many-body physics, but an effective immersion gap. But one good thing about this system is that you can just exactly diagonalize and numerically study it as well. So this is a plot of residual energy as a function of the velocity, and you see for large enough velocity, basically you are in a homogeneous regime. And you see that there's residual energy pretty substantial, and you can go to basically 6 or 7 order of magnitude a smaller residual energy by going to a smaller velocity. And it's interesting that for different disorder, the amount that you can drop that suppress the defects is different. So, and this is like homogeneous schedule is completely blind to this. And I thought this is pretty fascinating. So this is like becomes a probe into seeing different degrees of complexity that is hidden by a homogeneous schedule. So we did a landscape study of this, basically looking at residual energy as a function of velocity and alpha. And you can see that monotonically for a smaller velocity, you get better performance. So these are 4 different time scales. So here, actually, the time scales are associated with the units of J1, H bar 1. So this is, and the interesting feature is that for alpha, you see this dip. There's an optimal for a longer time scale, which is really gets you to extremely low energy sectors. And if you compare it with the value of alpha 0, which is here, and alpha around 3, that is one single spin update, you get 5 order of magnitude improvement. So, but we have like a phenomenological theory to understand what's going on. So basically, you can drive a different condition, like a base similar to a adiabatic theorem. You can define like a quasi-adiabatic condition. Is that instead of saying that what's the maximum velocity that I can go through a second order phase transition for a system that has a small gap, here you can go say what is the maximum velocity that I can go to get the maximum to have like the maximum correlation length. And this is related to a gap, like a square of a local gap instead of the global gap. And here, the derivative of the Hamiltonians as a function of, with respect to the parameter, a position parameter of a spin in the, where that actually at that particular time is experiencing the phase transition. That's basically the center of that wave front. So this is, I think, the most interesting property is that you can see a universality for the shape of the critical fronts. If you plot various distributions of various different instances of disorder spin, so each plot here is 1 million points for 1,000 different disorder system. Each one you get 1,000 different sample, and you see that here they have for different value of alpha, they just sit on top of each other. And so it's independent of the shape of the alpha. So you have this universal property. You can compare this with this expression that is and the same universality class based on the strong disorder renormalization group techniques, that you can see this kind of emergent universality parameter. And here, instead of n, you have an effective length scale for the system. So basically, you engineer your universality class by engineering your effective length scale. I think this is pretty interesting. And the gap is not the global gap, it's the local gap of the system. So if you look at the complexity of this algorithm, so this is the time complexity as a function of the inverse residual energy. It's all normalized because we are looking at the various different sizes. So if you at the very large value in the horizontal axis, you get the ground state. For a very small value, you have maximum error. You see that for the homogeneous algorithm, this goes like exponentially. So to get to a lower and lower energy sectors, you have to try it exponentially for an inhomogeneous protocol. This is a more fancy version of the inhomogeneous protocol that I didn't mention it. There's no time to go into that depth. That you get basically a polynomial scaling. And this is, I think, the most interesting one to look at this data. This is if you sample from like a linear chain of like 1,000 spins, and you have a strong disorder, so the J's values are anywhere between 0 and 2. This is equivalent to -1 to 1 for a 1D system. You see that for homogeneous schedule, you see this is a probability distribution of defects, and they're just sitting at various places randomly, and there are a lot of them. But in this kind of inhomogeneous schedule, you see that it's being very cleaned up, so you have way less errors. And the errors, the most interesting part is that the errors are sitting on the weakest possible link. So for thousands of these errors, you get the same kind of penalty in the energy as one of these errors here, where it corresponds to a big Jij. So this is a very low cost thing. So basically sweeping the defects from where they are very costly and dumping them into the sink of where the Jijs are very weak. So you pay a smaller penalty. So of course, you might ask, so how about higher dimensions? So we did some, this is a preliminary result of simulations of quantum Monte Carlo simulation that actually Sergey did on 10,000 qubits. So these are islands of 50 by 50 disorder ferromagnets separated by a spin glass border, a very weakly glassy border. And you see that here the quantum multicolor simulation shows this is the x-axis is like various different islands of this kind of ferromagnetic islands. And you see the median residual energy, and there are up to 2 orders of magnitude improvement with this strategy over a homogeneous one. So homogeneous is this red one, and you see that the different alpha for inhomogeneity is very low. And of course, we tried for more realistic, that was like a contrived example, for more realistic, like a glassy disorder, strongly glassy 2D cases. And you see that these are the results for 2 different instances. And you see that there is always an alpha that is a non-zero alpha, which is optimal, basically. And so basically alpha 0, the slope of homogeneity when you approach the standard adiabatic quantum computing, it looks suboptimal. For this, you have to do a little bit of pre-processing, which is like some cluster finding algorithm, which is like it could be n log n in the number of qubits. So basically, this is the conclusion of this, work. You can consider the possibility of that we have a new class of algorithms that are inhomogeneous in space and time, and you can drive the system quasi-adiabatically over a second-order phase transition. And there is an optimal shape for the critical point, critical front, and the length scale of inhomogeneity leads to an effective size of system which has universality, and residual energy can be minimized by several orders of magnitudes. And so this is obviously has application to approximate quantum optimization. Thank you.
Thank you for the nice talk. I can see how this would work for when you are trying to solve a homogeneous, like a ferromagnetic problem, because one corner can guide the rest of the problem in the right solution. But if you want to solve complex problems like spin glasses, if you start from one corner and let that corner guide the rest of the problem, you may not get to the right solution. How do you do that?
So basically, this is the result I showed. This is a glassy. This is the, these are -1. This instance that I have up here, this is -1 to 1, like 1 and any value between -1 to 1, not only those 2 values. So, and it's a strongly disorder, strongly glassy, and still it performs better. The only things you have to have is that you have finite correlation lengths. If your correlation, you are you have an underlying assumption in your question. You are saying that if the correlation length is equivalent to the size of input, how do you get any advantage? You don't. So basically, in worst cases of NP-hard, like this is not going to provide any speed over homogeneous. So as you approach like very large correlation lengths. But if your correlation length is finite, as you increase the size of system, this algorithm plays a dominating role. Because basically it tells you this is related to the area line, in physics, is that basically saying that all the information related to these boundaries, even for a hypercube. So everything you need to know about the system can be captured over a finite correlation length. So then you drive it with like a wave, and you just propagate and you get maximum. You can actually recover the ground state like that. Basically, this algorithm allows you to always get the ground state with a non-zero alpha, always. So basically, for any degrees of complexity. So as far as the correlation length is finite. So because you can engineer the wavefront to capture whatever correlation length you have. So you need to, this is the way we want to use it in the kind of, that actually this idea led to the quantum paratempering algorithm that, Hartmut mentioned this morning, is in a way that you can engineer this within that kind of things by looking at the replica, looking at the autocorrelation function, you can see how much correlation you have and then plug it in various inhomogeneously.
Doesn't it depend on where you start? Because I can design a problem that the corner you start lead to wrong solution, and then you try to align the rest of the problem to that solution.
Yeah, so listen, as I told you, the core idea is not to get the ground state. You might get states that have very small overlap with the ground state, but they're extremely in the low energy sector. So this goes to the, I would say the motivation of my, this slide. That, yeah, you're right. This is a good question. You're saying that I can see situation that you're nowhere close to the ground state. Yeah, you're right. But the still energy is very low, because you have very few defects. But these kind of pieces of like a spin chain or like a spin configuration, they could have a completely different overlap. The orientation with their ground state. So the fidelity with the ground state is small. I think this is good enough. Yeah.
All right,
Thanks.
let's thank Masoud once more.